Dear students, let us continue our study in this paper Organic Chemistry, and in this particular module we shall study about the reduction by using metal hydrides, and we shall continue this discussion in the next module as well. So, this will be reduction by metal hydrides part 1. Dear students, after studying this module, you shall be able to become familiar with an overview of different categories of reductions and the reducing agents which are used. You shall be able to understand the reduction via hydride transfer by the use of lithium aluminium hydride and sodium borohydride as the hydride reducing agents. You shall be able to differentiate between the selectivity and reactivity of lithium aluminium hydride with sodium borohydride, and you shall be able to be familiar with some other reducing agents like sodium cyanoborohydrin, diisobutyl aluminium hydride, which is abbreviated as dibal, diborane, and superhydride, that is lithium triethyl borohydride. And you shall be able to comprehend how the heteroatom carbon multiple bond reduction takes place by the metal hydrides for carbonyl compounds. Let us begin with going into recap of what you have already learned about oxidation reduction. Oxidation reduction reactions are vital for biochemical reactions and industrial processes. The redox reaction includes the electron transfer system in cells and oxidation of glucose in the human body, to name a few. Redox reactions are typically used to reduce ores in order to obtain metals, to name a few applications of reduction. Reduction is generally done either by catalytic hydrogenation or it can be done with the help of metal hydrides. Catalytic hydrogenation, as you are already familiar, is achieved by the addition of hydrogen molecule to the compound under the influence of a catalyst. The reduction by metal hydrides, on the other hand, is carried out by transferring hydride ion from the metal hydrides to the substrate. And many reducing agents are available, but our main focus of study in this particular module will remain on metal hydrides. Going further, if we talk about a hydride is basically an anion of hydrogen, that is H minus or hydride ion, or more commonly an alloy or compound having one or more centers of hydrogen having nucleophilic, reducing or basic properties. In hydrides, the hydrogen is linked by more electropositive element or group, and they are known for their reducing properties. The two well known hydrides, if we talk about, they are lithium aluminium hydride and sodium borohydride. They both contain polar metal hydrogen linkage, and this is because you are having the aluminium or the sodium and boron which are electropositive, and the hydrogen then they are as H minus, and that is why they are both hydride donor reducing agents, and we will see that they are considerably good reducing agents. And there are other examples of reducing agents which contain hydrides in them, and they are also commonly used as reducing agents in chemical synthesis, and they are, as you can see here, that can be dibal, that is diisobutyl aluminium hydride, sodium cyanoborohydrin, superhydride which is lithium triethyl borohydride, and diborane. The reduction reactions achieved by metal hydrides involve the carbon oxygen double bonds, carbon nitrogen double bonds, and the carbon nitrogen triple bond. The mechanism involved here is very easy as compared to that of the addition to the carbon carbon multiple bonds. As the double bond of the carbon oxygen or carbon nitrogen double or triple bonds are strongly polar due to the electronegative oxygen and nitrogen respectively in them, the carbon always is at the positive terminal. and this is exceptions are isocyanides that you have to keep in your mind. So, hence in these cases what happens is the orientation of the unsymmetrical addition to these bonds is very obvious. So, nucleophile or the nucleophilic species, they always get attached at the carbon which is the electrophilic species in these particular doubly or triply bonded cases, and that is how as the H minus will attack on the carbon, the electron pairs will move towards oxygen or nitrogen, that we will study in detail, and that is how the addition of hydride starts. So, keeping these things in mind, let us discuss the reaction of carbon oxygen, carbon nitrogen double bonds and the carbon nitrogen triple bond one by one. Here we shall discuss the hydride reduction of carbonyl compounds only, the hydride reduction of carboxylic acid, their derivatives and nitriles we shall discuss in the next module. So, let us begin with revising what are the various reduction methods. Reduction in simple terms indicates the addition of hydrogen to a molecule, that you are already familiar. And a very common reduction example, if you consider, as you can see here, is the reduction of aldehyde to primary alcohols. For example, here as shown is the propanol getting reduced to propanol, and this is done by the help of hydrogen gas in the presence of a platinum catalyst. So, before studying about the hydride reducing agents in detail, let us be familiar about some different methods of reductions. So, they include catalytic reductions, the hydride donors, etc. Let us try to know more detail about the catalytic reductions. As the name suggests, it is a reduction with the help of catalyst, and here hydrogen is added to multiple bonds in the presence of catalysts like platinum, nickel, palladium, etc. The choice of metal catalyst depends upon the compound to be used. Hydrogen gets absorbed on the catalyst surface and hydrogen addition takes place in the form of a radical, that is, in all the catalytic reductions it is the 2 electrons and 2 H plus which are added as 2 hydrogen radicals, and this addition, if you recall, is sterically controlled and leads to syn addition always. Catalytic hydrogenations are totally chemoselective and are often chosen for this purpose over other methods of reduction. One example you can see here, the cyclohexanone with hydrogen in the presence of platinum is getting reduced to cyclohexanol. On the contrary, hydrogenation can also work with nickel, rhodium or ruthenium. So, if you look at as shown here, if the depending upon the substrate, usual choice of metal that you have to pick is as shown here. Benzylamine or ethers we prefer palladium, with alkenes we can take palladium, platinum or nickel, and for aromatic rings it is the platinum or rhodium or nickel under high pressure. Temperature condition greatly affect the hydrogenation of various functional groups. At lower temperature, if two functional groups are present in the same molecule like the carbonyl and alkene double bond, only the alkene is reduced and the carbonyl remains unchanged. So, for example, you can see in this equation that starting with this aldehyde having a double bond also, the double bond gets reduced, but the aldehyde functional group is retained as such. But at higher temperature, both the alkene and carbonyl, they get reduced to alkane and alcohols respectively, as you can see in this particular equation. You have also learned about some important named reduction reactions like Rosenmund reduction, and you can see one example if you recall that where COCl gets reduced to CHO and not further reduced to CH2OH, and notice that here the COCl is getting reduced to aldehyde and the aldehyde is not further getting reduced to alcohol in this partial or the selective reduction where the poisoning happens due to this combination of hydrogen, palladium, barium sulfate and quinoline. So, there is a reduced level of reduction which happens with this combination, which is Rosenmund reduction. And notice another thing here, in this case the aromatic rings are not reduced. Another named catalyst you are already familiar is the Lindlar's catalyst, and the Lindlar's catalyst is the palladium, calcium carbonate and lead acetate. So, in the presence of this, as you can see here, the alkynes, they will get reduced to only alkenes, and the further reduction to alkane will not be happening. So, the product obtained in this case is an alkene, and that is what is being shown here. And notice again here there will be syn addition which will be happening. Another named reduction or the reducing agent that you have heard about is the Adams catalyst. Adams catalyst is formally platinum oxide, and this catalyst is not oxide of platinum, but the platinum metal that forms by reduction of platinum oxide to platinum during the hydrogenation. And Raney-Nickel is another catalyst that you are familiar with, and this is often abbreviated as RANI, and this is nothing but it is a finely divided form of nickel freshly made from a nickel aluminium alloy. The aluminium here is dissolved away by using conch aqueous NaOH, whereby the nickel will be formed as fine powder, which is then further washed and then heated to make it dry. After the catalytic reductions, let us talk about electro reductions and metal reductions. In this category of reduction, the metal gives an electron and solvent gives a proton. That is, the 2 electrons and 2 H plus are added alternately step by step, as one electron will add, then H plus, another electron and then H plus. And this is thermodynamically controlled reaction, and many metals have been used under this category of reductions happening, like sodium, magnesium, zinc, tin, etc. And these are done in the presence of either acid or alcohol, because metal plus acid or metal plus alcohol will be liberating this nascent hydrogen. And under this, a very common and a well known named reaction which you have heard about is the Birch reduction. So, what happens in the Birch reduction? The reduction of double bond systems and usually of the aromatic rings, that can be done with lithium or sodium in liquid ammonia, and this is called as Birch reduction. And what happens here is the solvated electrons, they obtain from easily ionizable group 1 metals in ammonia, and they are employed as reducing agents, and this reaction is highly regiospecific. So, as you can see here, lithium will be going into Li plus by liberating electron, and this electron in the ammonia medium will be solvated, and further it will give rise to the hydrogen gas and go into NH2 minus. So, Birch reduction works for alkynes too, and it is a good way of reducing them to trans double bond. So, here if we recall, cis products were obtained from Lindlar's, but in this case the Birch reduction you will get the trans alkenes. And one thing you should keep in mind is the phenols and the isolated double bonds, they cannot be reduced by this method. And if you look at some examples, the reduction of benzene rings will happen and you get this product. Alkynes to trans alkenes happens as it is shown here. Reduction of esters can be done into corresponding mixture of alcohols, and then this is known as Bouvelle-Blanc reduction. Now, coming to the next category and where the focus of this module is lying are the hydride and complex hydride reductions. In hydride reduction, the hydrogen addition takes place as hydride ion followed by the proton, that is H minus and H plus, and the hydride here is dominated by metal hydrides. And if we talk about examples, for example, aldehydes and ketones can be reduced by sodium borohydride or lithium aluminium hydride into corresponding alcohols, as you can see here. The examples are shown where formaldehyde, any other aldehyde or ketones are shown to be reduced and giving you corresponding alcohols. Then we can also do the reduction with non-metal compounds. Reductions have also been carried out by non-metal compounds such as HI, hydrogen sulfide, ammonium sulfides, diamides, hydrogen, etc. as reducing agents. And another category of the reduction by organic compounds, and these reductions are carried out by using organic compounds such as alcohols, organometallic compounds, etc. as the reducing agents. So, out of all these categories of reduction, our focus in this module is on hydride reduction. And if we talk about what are the most common metal hydrides, two names come to our mind: lithium aluminium hydride and sodium borohydride. So, sodium borohydride and lithium aluminium hydride, as you can see in the structures, they are shown here, and they are the most common hydride reducing agents. But notice that these are complexes. It is not the H minus S free, but it is a complex. In sodium borohydride it is the Na plus with BH4 minus, and in lithium aluminium hydride it is Li plus with AlH4 minus. If we talk about their preparation, Schlinger and Brown and their co-workers, they have mentioned the synthesis and some application of lithium aluminium hydride for the reduction of organic compounds in way back in 1947. Lithium aluminium hydride is prepared by the reaction of lithium hydride with aluminium chloride, and sodium borohydride can be prepared by the reaction of sodium hydride with trimethyl borate, that is BOMe thrice. And if we compare these two, there is a lot of difference in terms of reactivity of sodium borohydride and lithium aluminium hydride, as we can look it in this tabular format. In sodium borohydride, the boron part being of second period makes shorter and stronger bond with hydrogen. On the other hand, in lithium aluminium hydride, aluminium being part of the third period, it makes longer and weaker bond with hydrogen. And as a result, in sodium borohydride, the BH bond of NaBH4 has more covalent character. On the other hand, the AlH bond in lithium aluminium hydride has more ionic character. In case of sodium borohydride, it is less reactive as compared to lithium aluminium hydride, which is more reactive. And out of the two, if we talk about their basic strength, sodium borohydride is a weak base. On the other hand, lithium aluminium hydride is a strong base. Lithium aluminium hydride is known to be a very powerful reducing agent for organic compounds having polarizable functional group. They are stable at any temperature, but with moisture it gets converted into hydrogen gas, lithium hydroxide and aluminium hydroxide. The lithium aluminium hydride is usually stable at normal temperature, and in the presence of moisture it is destroyed, as I told you just now, because of this reaction taking place. So, hence the reactions for reducing organic compounds, when we take these reducing agents, is done in the presence of dry ethereal solvents like THF or ether. Now, let us extend our this knowledge and apply it to various functional groups. So, in general, the reduction of functional groups encompasses a range of reaction types and are classified into groups depending upon the type of bond undergoing reduction. So, we will be studying about the various heteroatom like nitrogen, oxygen with carbon multiple bonds. So, it can be double bond or triple bond, and we will see the impact how the metal hydrides will be carrying out the reduction over these functional groups. So, these groups that we will discuss are carbonyl, acids, esters and nitriles. But in this particular module, we will study about carbonyl group, and in next module we will be taking the other remaining groups. So, first of all, studying about the reduction of carbonyl groups. Carbonyl groups gives variety of useful derivatives. You are already familiar that they mostly undergo nucleophilic addition reactions, in which a nucleophile is attached first to the carbonyl carbon, followed by a proton usually taken, and that is how the addition to the carbonyl bond takes place. So, in the carbonyl group, the oxygen atom, as you are aware, is electronegative, and this results in the carbon oxygen double bond polarization. And due to this polarized nature of the carbonyl group, it is very reactive and it will be easily attached by the nucleophilic species. So, the electrophilic carbon atom of the carbonyl group, if we talk about hybridization, as you can see here, it is sp2 hybridized and it is planar or flat, and this makes it relatively unhindered and open to attack from either up or down side. Being planar, it can be attacked from either of the sides. So, let us look at the reduction by hydride, where the hydride is coming from NaH, NaBH4 and lithium aluminium hydride one by one. A negatively charged atom like hydride ion can act as both nucleophile as well as a base. So, whether a hydride ion will act as a nucleophile or as a base, it depends upon the reagent used. So, if we consider first the sodium hydride is an ionic compound, and hydrogen from sodium hydride is very small in size and has high charge density. It only reacts as a base and not as a nucleophile, and this is because the contribution of hydrogen atom to the sigma star orbitals of the HX bond, where X is any other atom, and the filled 1s orbital is ideal for interaction. Instead of this, 1s orbital which is filled is very small to link with the carbon's more diffused 2p orbital contribution to the lowest unoccupied molecular orbital, which is pi star of the carbonyl group. So, adding the H minus to the carbon atom of a carbonyl group would yield an alcohol and shall be a very helpful reaction, but the carbonyl reduction to alcohol cannot be done with sodium hydride. So, what can be added to achieve this? The simplest answer is NaBH4 or lithium aluminium hydride. So, now we study the sodium borohydride with carbonyls, how the impact will be. It is a water soluble salt that contains tetrahedral BH4 minus anion, which is isoelectronic with methane, and there is a negative charge on BH4 minus, you can notice this, and this is because boron contains one less proton in the nucleus than does the carbon, if we talk about the analogous CH4 which is neutral. So, though no hydride ion H minus is actually involved in the reaction, the transfer of an atom of hydrogen with an attached electron pair can be regarded as hydride transfer. And in other words, you can say from the BH4 minus, one of the hydrogen with electron pair is getting transferred to the carbonyl carbon. And note that it is the hydrogen atom that forms the new bond to the carbon, and this reaction can be shown with the arrows as shown here. And this results in this oxyanion, and the oxyanion so produced in this initial step helps stabilize the electron deficient BH3 molecule by adding to its empty p orbital, and as a result a tetravalent boron anion is produced again, which in turn transfers a second hydrogen atom to another molecule of aldehyde as it is shown here. And this process can continue in principle, so that all the 4 atoms of hydrogen could be transferred to molecules of aldehydes one by one, but in practice all the 4 atoms of hydrogens are not actually transferred. So, the first step is carried out in the presence of ethereal solvents like THF and diethyl ether. The water or alcohol is then added in subsequent step to work up the reaction, and this is where there is a proton which is given from the solvent, which is water or alcohol, for the alkoxide ion to take this proton and get it converted into alcohol. And this you can see, this is how the reaction is happening, that is the resulting alkoxide ion finally will be getting converted into alcohol. Sodium borohydride, it reduces both the aldehydes and ketones, though the reaction with ketones is slower. For example, as you can see here, benzaldehyde, it is reduced about 400 times faster than acetophenone in isopropanol as solvent. Sodium borohydride is one of the weakest hydride donors available. In fact, almost no reaction with water is evidence of this, else it would have combined with water just like NaH, where H minus would have acted as a base. Talking about specificity, sodium borohydride is a specific reagent and does not attack on carbon-carbon double or triple bonds of alkenes and alkynes respectively, as they are not sufficiently polarized. So, if multifunctional groups are there like carbonyl, alkene and ester in a molecule, sodium borohydride will reduce only the aldehyde or ketone functional groups and will not have effect on double or triple bonds of alkene or alkyne. For example, look at this particular case. In this molecule which has ketone, alkene and ester, only the ketone group is getting reduced to corresponding alcohol group. The carbon-carbon double bond as well as the ester functional groups are unaffected. There can be steric approach to control reactions also. For example, consider this reduction of NOR-camphor, and in this case the less sterically hindered exo attack is dominant, and this gives rise to endo-alcohol as the major product over the exo alcohol. After the sodium borohydride, let us see how the lithium aluminium hydride will be acting as a reducing agent for the carbonyl compounds. So, in contrast to sodium borohydride, lithium aluminium hydride is a stronger hydride donor reducing agent, and it has the tendency to combine rapidly with water as well. Lithium aluminium hydride is more electropositive than boron in the sodium borohydride, and that is the reason why the hydride from lithium aluminium hydride is more electron rich, and thus it is a stronger base in reaction with water and also a stronger nucleophile when reacted with functional group like carbonyl groups. So, let us look at both the action. In its basic action, lithium aluminium hydride will react violently and dangerously with water, and similar reaction can take place with milder groups like carboxylic acid. So, as you can see here, the equation showing how LiAlH4 will be reacting with RCOOH. Coming to the nucleophilic action, in its nucleophilic action of hydride, lithium aluminium hydride reduces all types of carbonyl groups like aldehyde, ketones, esters, carboxylic acids and amides. Aldehydes and ketones are reduced to primary and secondary alcohols respectively. If we try to understand the mechanism of reduction of lithium aluminium hydride, you can clearly see here that AlH4 minus, the H will be transferred as H minus to the carbonyl carbon, and as a result we have this alkoxide attached to aluminium, and with another mole of RCHO it will be giving you this particular species, and further and finally after hydrolysis there will be formation of this corresponding alcohol from the alkoxide part, that is RCH2O minus will get converted to RCH2OH. If we talk about what are the groups which are not affected by lithium aluminium hydride, there are functional groups which are not affected by lithium aluminium hydride like nitro or halides. And yes, this also will not be having any impact on the double or triple bonds of alkenes or alkynes, just like sodium borohydride, and as well as on the aromatic ring. Other metal hydrides, if we talk about, when the hydrogen of LiLH4 or sodium borohydride is replaced by either alkyl or alkoxy group, they can lead to formation of variety of reducing agents. And since lithium aluminium hydride is a powerful reagent, it is much less chemoselective than most of the other metal hydrides, and consequently other metal hydrides are generally used when chemoselectivity is desired. And in order to achieve the chemoselectivity, a number of less reactive or we can say more selective reagents, they have been prepared by replacing some of the hydrogen atoms of LiLH4 with alkoxy group. And how this can be done? This can be done by treatment of LiLH4 with alcohol. And most of these hydrides of metals are nucleophilic reagents and they attack on the carbon atom of the carbon hetero single or multiple bonds. For example, by enhancing the metal hydride into sodium cyanoborohydride, ammonia mediated reductive introduction of amine group to aldehydes to produce primary amines, and this was specifically achieved without the occurrence of byproducts of secondary or tertiary amine. So, this you can see here how the aldehyde ketones can be converted into these primary amines. And in general, it is always better to use the mild conditions possible for any particular reaction to reduce the potential for unwanted side reactions. Reduction with sodium borohydride is a lot easier to handle than lithium aluminium hydride. For example, it simply dissolves in water, whereas you have to be cautious, lithium aluminium hydride will catch fire even if it gets wet. So, hence sodium borohydride is more commonly used to reduce aldehydes and ketones, although lithium aluminium hydride works very well, but in that case proper handling is required. So, we will continue our discussion of this in the next module, where carboxylic acid and the other functional groups we will consider. So, dear students, let us now summarize what we have learned in this module. We studied that reduction can be achieved either by catalytic hydrogenation or with metals or with metal hydrides or even with organic compounds as reducing agents. And we studied in detail about the commonly used metal hydrides, which are lithium aluminium hydride and sodium borohydride. And out of these two, we studied how LiLH4 is more powerful and comparatively less selective hydride transfer reagent as compared to sodium borohydride. But yes, if we talk about the functional groups, the LiLH4 will reduce carboxylic acid, esters, lactones and hydrides to corresponding alcohols as well as amides and nitriles. But on the other hand, sodium borohydride will be attacking only the aldehydes and ketones and not affecting the carboxylic acids or esters or lactones or anything. So, sodium borohydride reacts slowly, but it is more specific in its action, it is more selective in its action, and this reduces aldehydes and ketones to corresponding alcohols without affecting alkenes, alkynes, esters, epoxide, lactones, carboxylic acids, nitro and nitriles.